Hi everyone. My name is Rade. I'm actually senior project manager in ALEC, and I work a lot with Encardio because we have the same problem. We share the problem. So I am usually working on complex projects that require monitoring. And as you could see from previous presentations, monitoring is usually related to long-term trends being closely watched that enables you to understand how building behaves through the long period of the time. But building is actually with us during construction for a very short period of time. And what we don't realize is that the building is very unsafe while it's being constructed. When the building is constructed, usually all the assumptions and predictions of an engineer are met. Building is integral. But when the building is in construction, when building is not completed, have a tendency to have different issues, which we need to closely watch. So we together choose to talk about Za'abeel because Za'abeel has a lot of complexity in terms of structure, in terms of methodology, in terms of monitoring, in terms of analyzing that data. And something that we spoke about already a lot here is decision making. In Za'abeel, decision making was supposed to be performed within minutes. So we had large information to be analyzed within minutes now, and the call was made, and we were right. So good, it worked.
Thank you for that.
Now, what are usually reasons, what triggers monitoring? Why we need to monitor? First is obviously safety. So if there is a potential that some building behaves in an unpredicted way and any kind of incident could lead to a loss, whether of life or financial loss, usually we monitor. We want to make sure that's safe. Then complex structures. Complex structures have this ability to have different load paths, different behaviors, all sorts of different information and different properties that have to be monitored because we can't establish what the building is doing if we don't measure, if we don't listen to the building. Next thing is challenging environment, which UAE definitely is. It's different temperatures compared to the rest of the world, very aggressive for corrosion, and so on and so on. So that's another trigger. Aging and fatigue, it has been elaborated extensively before. And then design uncertainties. So engineers want the building to behave in a certain way, but then in combination with environmental factors, the buildings have a tendency to behave differently. So we need to make sure that everything is within what we need. Obviously, some buildings have to be monitored because the law says so. For example, long-span bridges or nuclear power plants or whatsoever. So all of these trigger the necessity for monitoring. So usually what we do, we have periodic inspection and we have structural health monitoring. Periodic inspection is when we send an inspector, an expert goes there, checks how the building is, and makes a conclusion. The structural health monitoring is when we monitor through all of our technology today and we create a massive quantity of data, obviously. Now, what is the positive and negative side of all of this? So when it comes to periodic inspection, where we send engineers to see what's going on, the problem is that it's just a snapshot in the lifetime of a building. So it's just one moment that we recorded. We do not know what happens with the building the rest of the time. Second, we rely on the knowledge of the inspector, his skills, his ability to say, okay, there is something wrong. For example, I don't know if you followed the case in Italy. In 2018, there was a bridge that collapsed. That was only 2 months before that inspected, and was fine. It wasn't. So Also, it's not suitable for trend analysis. You don't see how the building trends if you have inspectors visiting from time to time. On the other side, the structural health monitoring is data interpretation, because opposite to periodic inspection, technology bombs you with information, huge amount of information. And this is the problem, because you have to use some other tools now to make sense out of this information. And also maintenance, which with technology progress now, it's the second concern is really reducing now. We can say that the maintenance is minimal. So the monitoring of the permanent condition, building in permanent condition, wants to answer a question: is the structure affected by aging, and does it behave as expected? And that's what we usually use monitoring for. But a less known use of monitoring is during construction, which aims to answer: is the structure safe at all construction stages, and does it behave as expected? And this is way more complicated than monitoring the structure in a final stage, because structure in a final stage has only one behavior. During construction, it changes shapes, load paths, all these static systems, and so on and so on. And to illustrate that, we actually need just 2 photos. So this is one Za'abeel completed. Very elegant building, 2 towers, Tower A, bigger, Tower B, smaller, and laterally attached steel bridge. Very, very simple. If you look at during construction, is completely different. So you have half completed towers, you have bridge that is hanging in the air off the cables. The load path of that bridge is not through the levels where the tower is actually designed to take the load. It's completely different. You have podium that is not designed to take the weight of that bridge, yet you need to make that bridge on the podium. All of that is completely different than whatever this building was originally designed for. And in order to make sure that in every stage of construction this building is actually safe, we need to monitor this building, and we need to know that it's behaving the way we actually want it to behave. Now, to give you a little bit of a context, we need to get really into a bit of a specificum of this project. So one Za'abeel is located in Za'abeel area, and it's practically surrounded by very important buildings in Dubai, including the palace is in the proximity. When it comes to infrastructure, we have a main highway that roundabout takes, as of 2020 information, 650,000 cars a day. You have a metro line surrounded by very important streets, but the worst thing is it has a highway going through it. And this highway has to be operational throughout the construction period. In fact, the traffic on that highway was interrupted only for 3 days out of 5 years of construction. And that's a major achievement. Now you can see here that the highway goes in between the buildings, below the bridge. That was lifted. So very, very challenging project. Just to give you a feeling, so Tower A is 300 meters, Tower B 235 meters. The bridge is 225 meters. So bridge is essentially another tower just built horizontally. And the bridge final weight is nearly 10,000 tons of only steel structure. No concrete, no facade, nothing, just the steel. So why the structure is so complex, I can show you here. So we have a massive raft in the bottom, 3.8 meter thick, to 2.8 meter thick. The towers, obviously, and the podiums are made of concrete. But the bridge in between is purely steel, and a very heavy steel. We use so-called jumbo sections. So the thickness of the flanges of our profiles are 150 millimeter, which is the maximum. Then this bridge transfers the loads into the tower through this embedded steel system. This embedded steel system is creating a locally composite structure in the tower. And then through set of composite columns and transfers this back to the raft. So if we look at this structure, you can actually see that you have a simple concrete structure that sits on top of a heavy steel structure that sits on top of the composite structure. So this immediately tells an engineer that this building behaves very weird, very strange, yeah? So nothing here is actually simple and predictable. We essentially had, and this is one of the things, so on this project we had Nikken Sekai from Japan as engineer, we had WSP as supervision consultant, and we have ALEC as a main contractor, and although we all have different contract interests as companies, when you encounter a project like this, you see all of these engineers sitting around the table and scratching their head and saying, okay, we have to think about this. So, just again, to give you a feeling, the embedded steel in Tower A is 2,500 tons in only 3 floors of that tower. And another 1,000 tons in Tower B, only 3 floors, where the bridge is connected. This is how the 3D of the rebar and the embedded steel looks like, and this is all T40s. This column, for example, is 5.4 tons per meter length of the column. 5.4 tons. It takes 36 days to weld these two parts of the column together. It takes 1 ton of electrodes to do it. So, very, very impressive stuff. And for example, I'll give you one tip. This column, due to the solar gain at the tip, moves 40 milli daily. It moves left and right, and there is nothing that can restrain it because it's so strong. These are the nodes which bridge will be made of. I will show you in the next slide. So you can see human beings can sit inside of them. And now I would explain the methodology. So before I start the video, the highway cannot be closed. So that means we cannot construct over the highway. We need to construct everything on one plot. Then we need to incrementally launch the bridge until it goes over the highway. And when the bridge is completed, we will lift the bridge. So I hope the video will play now. This is the next slide. Can you play it? So this is the temporary structure on which we will build the bridge, and the bridge is built in segments. And then slide it. Now you can clearly see that the bridge design to be supported differently is becoming a cantilever. Very big cantilever above the road. And as we slide, we add new segments of the bridge which acts as a counterweight to hold this cantilever. The bridge continues being launched. We then remove the nose, which is the temporary structure. When the bridge is nearly completed, we install gantries on these towers, and then we install gantries for the rest of the bridge to be lifted at the end. Then this whole thing is lifted up. This is 8,570 tons in one piece. Then we assemble the last piece of the bridge, and then we strand jack that upwards. So from this video is very clear that this structure goes through incredible cycles and completely different stages compared to what the structure is originally made for. And obviously, when the engineer designed this for its final stage, he doesn't think about temporary stages. So it's very, very hard later on to make the structure fit for the purpose of construction. And that's why we need to monitor this life cycle. This video, I think, will show you now how this looks in real life in Dubai. You can clearly see. So this road is operational. Luckily, it's not a congested road, but I mean, the bridge was slided, and this was the moment when everyone was asking, what are you guys doing? Why is this bridge 45-meter cantilevered over a live highway, and they were surprised that you can actually drive below it, and it's hanging in the air. So eventually the bridge was completely, so in this stage you can see now it's continuously supported beam above the bridge. Very, very interesting effects of this launching. For example, when we are launching the bridge, you will see that the forces in the jacks rise, and then when we break the static friction, the bridge jumps, and it goes for 300, 400 millimeter, then it stops again. And then again, the force rises, and it goes like that. And then as soon as you think, okay, I learned something about this, this is how it's going to behave, the bridge touches the other side and starts behaving differently. Now these two structures start working as springs between themselves. So if the bridge slides on one structure, it pushes the other structure. All of this, we had to see the effects of all of this. So this is the video of the lifting the bridge now. Now, the lifting of the bridge is, again, completely different stage. It's a completely different project to sliding. Can you play this? So you can actually see how many monitoring points are all over the bridge. The bridge was lifted 2.5 days. First 10 centimeter took 24 hours. And that was very interesting with authorities because it was a challenge to explain why you need 24 hours for 10 centimeter, but you are promising 2 days to complete. Because when you do strand jacking of such a structure, if anything is going to go wrong, it's going to go wrong in first 10 centimeter. And that's where we play with forces, with deflections. The temperature changes in UAE drastically, so all of your data collected has to be tuned to accommodate for the temperature change, and so on and so on. Eventually, what I would like to explain, how do we perform these so complex activities, and where does monitoring sit in this? So this is an organization chart of a lift, and this shows you how the team functions. And this actually lifting, we simulate 2 or 3 times before we actually lift. We do fake lifting. So we have a control room in which experts sit. The main guy is called lifting master. This person makes a call. He communicates with all the teams based on the information issued by engineers. In those, we have technicians operating the jacks, people that actually control the jacks. We have engineers from different fields analyzing the information collected through the monitoring devices and monitoring teams, and then they make a decision. Now I want to tell you one interesting thing, a detail that is very important. The bridge, once lifted, cannot be lowered down. There is no reverse. It can go only up. So if there is something going wrong, you have to stop it on time, or it could go into a stage that cannot be fixed. Very dangerous. Horrible thing to do, frankly speaking. And you heavily rely on your eyes and ears, and those are monitoring devices. You heavily rely on them. Some of them have to be very traditional, very simple. Some of them have to be technologically advanced, but eventually they all need to sync, and they all need to talk same language and show same results. And that's why sometimes, to measure same parameter, we rely on a number of systems of monitoring. So if we look at this chart, you will see that we have A and B operators, these people that operate the devices, that we have logistic team. Electricity supply is extremely important. These machines consume huge amount of electricity. Health and safety, these are the emergency people that take action if something goes wrong. We have traffic control, people are ready to stop the highways if something goes wrong. But most importantly, we have these two teams. Survey and monitoring, which actually gives you an input, telling you what's going on with your structure, and the QA/QC people, those are that experts that we show in the beginning, people that actually go to the location and check with their expertise, how is the structure doing. Now to just give you an insight, these are the gantries that were used to lift the bridge. If you consider the tower a mast, this is a jib on the tower crane. The gantries accommodate jacks, cables, and huge amount of monitoring devices, because this is the most critical point. This is where all the forces travel. Also, you can see the bridge is connected this level and below. So these gantries are built on the part of the structure that is not meant to take the forces from the bridge. So this is extremely strained, extremely pressurized area of the structure. This is where the structure suffers the most. Now, this is how the control room looks like. For example, all of that buttons and lights are actually related to each jack lifting. We have 24 jacks lifting the bridge, yeah? So each jack can be operated, and it has to be operated in a real time. So you need to read your monitoring information on the screen and turn off and on jacks as required, 24 of them. So we had experts from Switzerland coming to actually operate this, because usually they don't use this many jacks. 24 jacks is really large number to be simultaneously used. We also managed to integrate in our system their monitoring devices. So they monitor two things. They monitor oil pressure and the laser distance. What this means, they have a gauge in a jack that measures the oil pressure, which actually is translated in the force applied. But because these gauges can be not functional, they have also a laser beam between 2 points on the cable, always measuring the distance and telling you, is your reading on oil gauge actually right? What happens if you have a jack that is lifting more than his other friends? He attracts more force and can cause local failure. This has to be avoided. So after some studies, we came to an amazing conclusion that towers will actually move a lot. What you see here means that not a single elevator can be installed in this building. 78 elevators will be completely dysfunctional. Tolerance of an elevator shaft is 30 milli. We are everywhere 35 up to 100 plus. What do you do with this building now? How do you deal with this kind of a thing? So once we lift the bridge, it's obvious both buildings will lean toward the bridge because it's 10,000 tons. What do? We build a tower that is not straight. And as far as I know, this was never done before. So we literally built towers that are leaning outwards. We preset towers vertically, hoping they will come back. Because no one ever did this. We contacted people from universities all around the world. We had experts, and no one ever did this. And you know, when you run these simulation models like SAP 2000 or ETABS or whatsoever, this is all theory. Especially when we know that the pre-camber calculated by engineer is nearly never accurate. So now you have to pre-camber, or actually preset the entire tower, hoping this is going to come back. So we had some resistance from traditional engineers saying, are you crazy? We have thousands of cubic meter of concrete per floor, and you think this is going to move? Not possible. Yet, there was no mathematical proof possible from any kind of analysis showing that the towers will not move. So we had to preset, and we did. So what this means, we actually, when we built the, you can play this video, please. Can you play the video? So when we build the towers will be built outwards, leaning outwards. We'll lift the bridge, and the towers will come back. Then we will connect the bridge, And then the further construction of this tower also has to be outwards. Because as you keep adding load, the towers keep leaning toward the bridge. And this was really tough analysis, really tough. After we finished this, we have to sit with an engineer, or actually number of engineers, and decide what parameters to monitor. What is the monitoring that we want, monitoring information we want to receive, but above that also what frequency and what method. All these three were very crucial. For example, we had to monitor with theodolite certain points on the tower. I know that today technology tells you, oh my God, you have point cloud. You have point cloud, you have make trillion of points per day. Why you don't use that? Try to analyze trillion points in 5 minutes. Not possible. Information you need to analyze is too much. So sometimes a method that is a little bit more traditional gives you more clarity. Engineers generally like to remove white noise from their thinking. They like to think simple. So we had devices that then have to be placed around the building sufficiently far that the building settlement doesn't actually impact the performance of these measurements. Because if your theodolites are close enough, when you lift, the theodolite base itself will be moved. So we had to go into other people's houses in the plots owned by RTA or Etisalat or all these important buildings around Za'abeel and ask them, can we please put something on your building? And they're like, what do you want to put something on my building? So it was very interesting from that point of view as well. Now, you can see how those were actually operated. Everything was automatized. So every 5 minutes, every 3 minutes, the theodolites will read around 300 points and send the information to a server automatically. Apart from the theodolites, we have strain gauges, we have tilt meters, we have all sorts of equipment in regular intervals sending information during the lifting of the bridge. We obviously ran these systems even before lifting the bridge in order to try to see the nature of the building, how the building behaves during different times of the year, how the building behaves when it's very humid, and so on and so on. So in essence, we performed monitoring from all sides. I will now go to the methods that we actually used. So strain gauges. We had strain gauges fixed on a number of steel members. We had system of monitoring prisms which were placed on the bridge and on the towers. During lifting, before lifting, after lifting, all of that was monitored. Except that we had embedded strain gauges in the concrete, trying to see how does the concrete structure behave during these temporary stages. Because remember, concrete is not designed to do this. Concrete was designed to be at the final stage. Then we had concrete crack monitoring. We knew that the concrete will crack. We knew that we will have elastic deformation of the rebar within the building. And we knew once we welded the bridge and released it, the cracks will close. And this is theoretical knowledge. In order to know, is it really like that? You need to monitor. When we monitored, it was like that. So all the cracks that appeared during lifting actually just closed at the end. We used, obviously, a number of prisms fixed on the concrete structure. We used tilt meters. Why tilt meters? Because the building will change the angle. And this was one of the first things everyone asked. Did building actually move? And interestingly enough, the building didn't move as they designed initially. It moved only like 70%, maybe. But then, when it went through 2 temperature cycles, means 2 days, the building actually reached the position. So it looks like, from what we understand on that project at least, that this temperature cycle of cooling and heating the building gets the building where the engineer calculated the building will eventually be. Then we use laser beams. This is extremely simple and extremely useful method. What we had, this was fixed to the raft, It's a laser that shoots laser up. In every slab of the 35 floors we built, we left the opening. That milky glass is fixed to the opening, and you can real-time see how the building moves as you lift. Very simple method, yet very, very successful. And obviously we had oil pressure gauges in the jacks that we used to see the force applied, and the thermal sensors in order to adjust the results. All of this now gave us input. For example, the bridge internal forces. We had to know how does this bridge behave when we are lifting it, and its deflection by using the prisms. Now, if you pay attention, you will see that more important is the information you want to get. More systems is used to actually gain the knowledge. Dynamic forces due to the incremental launching. We used forces applied by jacks and internal forces distribution. We used the jack pressure gauges. Temperature during the launching, during lifting, very important information. Bridge level and deflection during the strand jacking. So when you lift, how do you make sure that the bridge is not going this way or that way? You have to monitor this all the time and level it. So when we will perform a lift, we will perform 5 strokes of 500 millimeter. Then we will do the leveling. We will survey whole bridge. We will say the left side of the bridge is 5 milli down. We will just perform slight leveling, lock the jacks, and continue lifting. Then load path within temporary structure and tower during strand. This is the most challenging thing actually. Because the load in the tower that is not made for temporary stage could go anywhere. The engineer believes it will go here, but it could actually go anywhere. So the set of strain gauges we used told us in a real time, how does this work? Where is the force traveling? Are we overstressing something? And then concrete cracks progression, obviously monitored throughout. Tower shortening, also the towers were shortened down 20 milli. And then tower inclination change during the lifting. And you can see, because this is one of the most important parameters, we use 3 different systems. All of this information should give you more or less similar results. They cannot be perfectly equal, but similar. And what engineers actually look at when it comes to the results of monitoring is more, does it make sense, and is it in the magnitude it should be, then really is it accurate? If I give you a simple example, if you have 8 columns on the side of the tower, and during the temporary stage you know that the first column and the last column will attract 20%, and the rest, 80%, will be in the central columns. And when you look at the monitoring results, you might have different level of force, but that relationship between the columns should be same. You should not have 80% going on the external and 20 in the center. This is what they are looking at. As long as the building has a behavior in a way they predicted, it's okay, even though forces might not be exactly the same. Now, all of this, when you collect all of this, you get this. Horrible. Try to make a decision on this. Nothing. You don't get one, you get thousands of them. Hundreds if you want, thousands, millions. But nothing that actually tell you what is going on. It's just raw data. So then we sat with Encardio again and we say, okay, you know what? We have to develop a software that actually makes sense out of this information. It makes calculations for us that we did in our models, and it tells us, my friend, very simply saying, your tower went 20 milli there. Do you want it to go there? And that software not only that tells you that your tower did something, but also compares that to the stage you are in and what you was calculating initially for. So you said it will go 22 milli, it went 20, acceptable. You predicted it will go 22, it went 50, stop. There is a problem. And we did that. That looks like this. This is a software we developed together with Encardio called DNA. And this software, in a real time, gives you hundreds of parameters, actually, and it gives you a color code criteria, where if something turns red, all of that is red, not because the bridge is going to fall, it's because we just didn't start yet. But all of that gets red, green, yellow, independence. Are you approaching the border value, the limit you set? And for the end of this presentation, I will show you the video during the lifting. How do we operate the jacks? How in real time 16 engineers work reading these results and making decisions while the structure actually moves. You can play the video. So you can clearly see here, this is people operating, people communicating on the radio. They have cameras looking on the bridge and on the jacks live. As they operate the jacks, the camera now will turn around. You see here, they have also their own criteria set, where they show they have values expected in the jacks, so they make sure that that doesn't go away. On their computer, they have all that jack oil pressure and the distances being monitored. And you can see as he operates a number of jacks in the same time. Turn off one, turn off the other one, start again.
Okay, 45% now.
Now,
So we go 50%.
this is the monitoring team. This is the team of engineers sitting and reading the information all the time on all the strand jacks, on all gantries, everything, and communicating back to these people. We can proceed or we have to stop. So in order to achieve this, we had to sit together with so many experts in order to make this program at the end give sense to what we're doing and to make a right call. From steel people, strand jacking experts, Encardio as monitoring, us as main contractors, coordination with authorities, all of that was done thanks to this software. And I think that the future of monitoring is not in refining the technology in terms of devices only, but essentially enabling people to simplify the huge amount of collected data into something very easy to understand and to make quick decision. For us, luckily on that project, we managed to do that in a very short period of time, very intensive work, but we could make calls very quickly. Thank you, that's all from me.